So picture this. You've just built an amazing new AI for, say, a self-driving car. How in the world do you make sure it's ready for every bizarre, unexpected thing the real world can throw at it? I mean, you can't possibly test for everything, or can you? Let's dive in. Right, this is the multi-billion-dollar question in AI right now. Think about it, manually designing every possible test case, every weird road layout for a car, every cluttered room for a robot. It's literally impossible. You need a way to automatically find an AI's blind spots, its breaking points, before it's out there in the wild. And to really get a feel for this, just look at these two images. On the left, you've got a classic Super Mario level. It was designed by a human, right? It's fun, it's predictable. But on the right, whoa, that is a level designed by an AI with one single goal, to break another AI. It's meant to be bizarre. It's designed specifically to exploit every single weakness it can find. And that really gets to the heart of what researchers at the University of Southern California are digging into. They're trying to build a system that automatically generates this massive, diverse collection of really challenging environments. The whole idea is to find the failures in the simulation so they never, ever happen in the real world. So this isn't a totally new problem. People have been trying to crack this for a while. The existing methods were pretty clever, but, well, they had one really big problem. The main idea behind the old way is something called quality diversity optimization. Okay, it's a fancy term, but the concept is actually pretty simple. You don't just want hard challenges. You want challenges that are high quality. And by that, I mean they're actually solvable. And you want a huge diversity of them, so you're testing the AI from every possible angle you can think of. You know, the perfect way to think about it is like building a library of challenges. These older algorithms try to fill this library, making sure every single shelf has a book that represents a unique and difficult test. You want to cover every topic, right? From weird jumping puzzles to mazes that look easy but are actually impossible. But here's the catch, and it's a big one. As the researchers point out in the paper, building this library the old way is incredibly, painfully slow. For every single potential challenge, you have to generate a whole new environment and then run a full, time-consuming simulation of the AI trying to solve it. And you have to do this thousands, maybe even hundreds of thousands of times. It just grinds everything to a halt. And this is where the new breakthrough comes in. It's an algorithm called DSAGE, and its entire purpose is to find a really clever shortcut around that massive simulation bottleneck. The core idea here is just brilliant. Instead of generating a level and then running a slow-motion test to see if the AI can beat it, what if you could just look at the level and accurately predict how the AI would do? What if you had, like, an AI forecaster? And that's exactly what a deep surrogate model is. It is an AI forecaster. You train it on tons of examples. You show it an environment, and then you show it the real simulation result. And over time, it gets unbelievably good at just predicting an AI's performance by looking at the setup. It lets you skip the slow part almost entirely. Now, what's so cool is how this works in a loop. First, the super-fast AI forecaster predicts thousands of new challenges that it thinks might be interesting. Then, you take just a handful of the most promising ones and you test them for real with the slow simulation. And finally, you use those real-world results to help the forecaster learn and get even more accurate next time. Predict, test, learn. It's a cycle that just keeps making the whole system smarter and smarter. Okay, so the theory sounds great. It's elegant. But does it actually work in practice? Well, the researchers put DH to the test in two classic spots, a complex maze environment and, of course, Super Mario. Let's start with the Mario results. This graph basically shows you how well different algorithms did at finding new challenges. The more filled in the area is, the more unique challenges were discovered. And as you can see, that dark purple line for DSAGE, it fills in almost the entire space. It just absolutely blows the older methods out of the water. In the same amount of time, it finds a vastly bigger and more diverse library of challenges. It's not even close. And this is what that data actually looks like. This is one of the levels DSAGE created. Look at that staircase trap. It was designed by the system, on purpose, to test the Mario AI's ability to do a long, continuous series of really difficult jumps. That was a very specific behavior it wanted to test, and it built the perfect level to do it. And the same idea works in other places too. Take a look at this maze. I mean, it seems simple enough, right? But that yellow line, that's the path of a very sophisticated AI agent, and it gets completely stuck. DSAGE is just a master at finding these subtle, tricky layouts that exploit these really specific weaknesses in an AI's logic. So then the researchers decided to dig a little deeper. They compared a basic version of DSAGE with the full, souped-up version.
The full version was a little smarter. It didn't just predict the final score, it also tried to predict the agent's likely path through the level, giving it a lot more information to work with.
And the result? Well, it turns out those extra components made that AI forecaster way more accurate. And a more accurate forecaster means you find better, more diverse challenges, and you find them faster. It was a super clear demonstration that those extra little tricks made a huge difference.
This is all really fascinating stuff, but let's zoom out for a second. Because this isn't just about making unbeatable Mario levels. The real-world implications here are enormous.
Seriously, think about it. You could use this exact same technology to generate millions of bizarre, unexpected road scenarios to test self-driving cars. Or you could use it to make sure a robot helper can still navigate your house perfectly, even if you move all the furniture around. This is a powerful tool for finding those weird edge cases and hidden vulnerabilities in any AI system. And that means building safer, more reliable AI for all of us.
And that's really the big takeaway. By using one AI to intelligently and automatically find the weaknesses in another AI, you create this incredible feedback loop. It's a system that generates the perfect tests all by itself, which allows us to build AI that is more robust and more trustworthy. In a very real sense, this is AI building better AI. So it leaves you with this one final, really provocative thought. We've just seen an AI that has mastered the art of asking the perfect, most challenging questions of another AI. So, what happens when we point this powerful question-asking ability at other grand challenges in science, in medicine, anywhere? What's it going to discover next?